Hello, I'm Matthew Brehove, and I'm going to be talking about our project, the Spiking Neural Network Modeler, also known as SPINMO, and how it can benefit neuromorphic computing at the edge. Chromologic is a boutique product development organization that applies a unique multidisciplinary approach towards innovation. Founded with partial funding from the SBIR program, Chromologic is a privately held company consisting of a team of highly educated world-class staff of 17 engineers and scientists, located in Monrovia, California. In 2010, Chromologic initiated the spin-off of Covice Us, which is an independent commercial firm focused on providing supply chain security services to the aerospace, defense, and medical markets. The Navy needs small, unmanned vehicles that can make full use of their onboard sensors by interpreting the data in real time. Deep neural networks have been shown to be capable of performing many of these data interpretation tasks, such as identifying and tracking objects in images, listening for particular sounds or words, facial identification, and RF source identification. However, for applications that need to operate on battery power for extended periods of time, using deep neural networks to analyze streaming data can become prohibitively energy intensive. There is an emerging field of neuromorphics which introduces new processor architectures that hold the promise of dramatically reducing the energy cost of continuous machine learning inference. This is made possible by biologically inspired data processing approaches that overcome the von Neumann bottleneck that causes conventional processors and GPUs to use more energy. We see this technology improving the effectiveness of unmanned aerial vehicles, unmanned underwater vehicles, and stationary sensor platforms. Neuromorphics is a potential solution for applications where the lowest possible power use is necessary and where speed is highly important. Some applications that come to mind are threat detection and localization, audio classification, visual depth perception, and power system fault detection. One of the most energy-intensive aspects of neural network computations is the von Neumann bottleneck, which requires that neuron weight data be repeatedly moved from memory to processor for each evaluation. Neural network processing of time-varying data, such as video, is also inefficient because all of the activations in the neural network need to be completely recalculated for each frame, even when there are few changes between frames. Lastly, for analog neural networks, the outputs of most layers are about half-zero values due to the use of the ReLU activation function. These zero values are stored, processed, and moved around the same as every other number despite not affecting the result. To improve on these inefficiencies, neuromorphic processors such as Intel's Loihi associate neurons with specific processor cores where the neurons' weights are physically located on the chip adjacent to the core. Loihi has 128 such neurocores that are networked together on the same chip, thus overcoming the von Neumann bottleneck. But these processors can't work with traditional deep analog neural networks. Instead, they run spiking neural networks, which are inspired by the way that biological neurons communicate in discrete timed packets of information called spikes. These offer huge speed and power savings advantages because the outputs of each neuron are only communicated if they are non-zero and only when change is taking place. Developing spiking neural networks is not trivial, however, and still an active area of research, which limits the use of neuromorphic processors. Therefore, Chromologic is developing SPINMO to convert trained neural networks into spiking neural networks in a unique and advantageous way. Current approaches of ANN-SNN conversion use rate-coded SNN network, in which the rate of spikes output by each neuron corresponds with the analog value of the associated ANN neuron. This is inefficient, both because it effectively uses repeated addition in place of multiplication and because it doesn't take advantage of temporal sparsity. It still requires computation to take place when the input stays the same. SPINMO takes a different approach by converting ANNs into sigma-delta neurons, which pass graded spikes between layers. The spikes represent changes in the layer's outputs and can be run on neuromorphic processors like Loihi. In this way, the converted sigma-delta networks take advantage of temporal sparsity, spatial sparsity, and memory proximity to processing, while allowing developers to work in their preferred coding environments, such as PyTorch and TensorFlow. We have a proof of concept running on conventional hardware, and on the right, we show how the outputs of a full precision analog neural network match the outputs of our converted, quantized, sigma-delta neural network. This shows the fundamental conversion operation that we're trying to achieve is possible. So far, we've shown that the conversion is possible, and we have written custom microcode for the Loihi processor that would allow the specific kind of sigma-delta neurons that we need to run. We have remote access to the processors, so the next step is to show the converted networks running on the processor remotely and then get the chip in-house so that the whole sensor-processor pipeline can be tested together. Finally, we need to engineer the completed system such that we can demonstrate the supremacy of our neuromorphic approach over conventional processing hardware while keeping the accuracy of the result the same. As I've noted before, our solution runs on neuromorphic processors and takes advantage of memory proximity and temporal and spatial sparsity, which all work to lower power usage and speed computation. Analog to spiking conversion is also, we believe, a key step in moving neuromorphic processors to regular usage because of the immaturity of direct SNN training. The next steps involve in-house demonstrations on streaming video data and the in-house chip that demonstrate the technology's advantages. We're hoping to have that test done at Nav Air in Patuxent River, Maryland. We're also excited about demonstrating the technology at Nav Air and identifying applications that would benefit most from low-power continuous neural network inference. Outside of the Navy and DoD, SPINMO has diverse commercial applications, ranging from photography drones to wearable electronics, robotics, and power distribution anomaly detection to autonomous driving. Any edge inference application is a potential application for SPINMO. We're proud to collaborate with Intel to develop SPINMO for the Loihi neuromorphic chip. We're actively seeking funding for post-Phase 2 work to adapt SPINMO for specific edge applications. And we're also looking for prime partners who share our goal of reducing power and latency in edge ML applications. If you're involved in projects that require efficient edge ML solutions, we'd love to talk to you. We're seeking relevant datasets to build and deploy solutions that make a difference. Thank you for listening.